Hi everybody. This is a correction to the fluffy cat video. I had made a mathematical error and I caught myself, but I didn't finish the problem. I was just going to redo it, and turns out I threw away the wrong solution and posted the incorrect solution online. So this is a cleaned up version of what we have going on. So we're going to start with our parsing. Oh, I was going to start down there, does it? Okay. And remember, our goal of parsing is just to get the problem statement into images and words that we better understand. So I start with a board, which is 8 foot long. And I had looked this up earlier. This is 2.44 meters. And this same board has a mass of 15.7 kilograms, which seems a little light for a 2x8. The problem is the board is held off the ground by 2 bricks. As shown, with the center of mass located here, let's say. Because that locates the second brick. Let me go back to black on that. And this gap is 0.33 meters from the center of mass. Notice, had this brick been drawn on the left-hand side of the center of mass, the board would already be tipped. So what's next is we're going to have a fluffy cat head, big ears, whiskers. Okay, tail. Let's see. And we're trying to figure out how far does the fluffy cat get from the center of mass. So what we're looking for is this distance x. And our fluffy cat has a mass of 7.2 kilos. Okay, so that has all the information out of the problem that we care about. We've got, yep, all right. So the question then becomes, let's go back to blue for this. Our question is, find distance cat. Gets from center of mass. It's also, in our case, finding x. We're talking about the board tipping. So if we go through our pink sheet, is there a collision or a shape change? No. Is there a rotation of a volume? Yes. Is there a time dependency given? No. Are there initial and final picks? No. So we can jump to the sum of the torques is equal to I alpha. So our approach from the pink sheet is to sum the torques and get I alpha. Now, the important thing to remember is that we want the moment just when the cat makes the board tip. And a couple of important things happen under the tipping condition in our case. First of all, it's a rotation, which means this board wants to rotate up if the cat gets too far along the board. So the whole thing's going to rotate clockwise. When that rotation happens, the normal force of the left-hand brick goes to 0. The board is being rotated off of that brick. So we go to red, and now we do our approach. And the first one we'll do is the one recommended. So we're going to do an approach where we sum our torques about a common axis, and that's going to equal to 0 because we're looking at the moment it begins to rotate, so alpha has to be 0 as well. There's no rotational acceleration in this case. Okay, so now what we need to do is draw a free body diagram of our system. And let's just make my up as positive. And x this direction is positive. Okay, so now let's attach forces to this beam. Oops, one more thing I wanted to denote, which was the center of mass. So let's build in our rotation now. Okay, so that's going to come from us having a force normal from brick 1, a force normal from the second brick. We're going to get a force of gravity, and we're going to get the force normal from the cat. So everything is held up, and let's go ahead and mark our lengths. Oops, not even mark our lengths, I'm sorry. We need to choose an axis, and that axis needs to be around a physical thing that's holding it up. While it's true we can use the center of mass as our rotation in free space where there's nothing holding anything in place, the fact is the brick is holding something in place. So our best choice for the rotational axis is around the center, is around that brick. So we're going to sum torques. So what we do when we sum torques is we make the table. We're going to sum our torques. So I got a rough start on that one. Let's try it again. We want to list our forces. We want to carry out the cross product and any arithmetic that will then produce a torque for us to sum. So we take a look at our forces. We've got the force on the far left. I've got a force of gravity. I've got the force normal one. And I've got the force of the cat. Which, even though it's a normal force, it's quickly going to turn into an mg gravitational force on us. So the force normal, our cross product says we go in the, let's get a different color for working in the box. So because torques are defined to be R cross F, and we've been using this wheel to figure out our torques. Let's go ahead and do the cross products for each of these forces. So the value of force no is going to be 0. So even though I can do a L over 2 for the distance, I'm going to be multiplying it by 0. So the cross product would be negative x hat crossed into a positive y hat going up. Because that's R cross F, we have to go, let's get my crayon out. I always screw that up. We have to go from there to there. So it's not even L over 2. We'll have to clean that up. Not at all, because we have the 0, so this torque goes to 0. The force of gravity is 0.33 because that's our distance from the axis to the center of mass. And we're going to multiply it by the force of gravity. But most importantly, we have the same negative x hat direction. In this case, crossed into a negative y hat direction. Because FG is pointing downward. We had to go negative from our axis to get to the location of the force, 0.33 meters, and FG is pointing downward. What we do with the minus signs is we take them and make them both positive. Negative times a negative is a positive. Then we go to our wheel and we start at x we have to go in the y direction. Grab y, and that's going to leave us with z hat. So I'm going to get 0.33 meters. The force of gravity. Let's just get the board in place so we don't lose it. And all this is happening in the z hat direction. The next force, our normal force, is at the axis of rotation. So R, in this case, is equal to 0, even though I would have a normal force. Let's get back to red in there. Red. All right. So we have 0 distance to our force normal 1. And we really can't even define the first term in this cross product. Because is it pointing in the negative x hat, or positive x hat direction? Who knows? Complicated philosophical questions we don't care about because it's equal to 0. Our last torque, its cross product is going to be the distance, x, the force of the cat, the distance x is in the positive x hat direction, the force of the cat, oops, that should be a cross product sign, not a plus. The force of the cat is pointing downward, so it's going to point in the negative y hat direction. So to calculate that, we choose our color. Okay, then let's get rid of the green one from now. And I start at x. I go in the direction of y, and I'm going to keep going until I find z. What about the minus sign, you say? Well, that gets carried out in front. It says -1 after all, so I can put it anywhere in the expression I want. And I'm going to wind up with a z hat here. Liking this purple, so we're going to sum the torques. And we're going to get 0.33 meters times the force of gravity of the board. And that's going to be, let's see, what was the mass of the board? 15.7 kilograms. And it's a force of gravity, so we put in the 9.8 meters second squared. And then that's minus x, and the force of the cat. Let's see, the force of the 7.2. So we put down 7.2 for the force of the cat. Everything is happening in the z hat direction. And we know from earlier it's equal to 0. Well, it's 7.2 kilograms. All right, so we do our calculation. 0.33 times 15.7 times 9.8 equals a nice clean 50.77 meters times newtons. Although that's the order for torque, it's easy to confuse this as millinewtons. So this gets expressed instead as Newton meter. Then we subtract from this, might as well set it equal, bring all of this to this side of the equation. And that's going to give me x and 7.2 kilograms. So x is just going to equal 50.77 Newton meters divided by 7.2 kilograms. And notice the big oops that I get with my units. The units for x, I'm in crayon mode, gosh darn it. The units for x really ought to be meters. But when I come over to this side of the equation, I get newtons, which are kilograms, meters, seconds squared. And I add a meter, and then I'm dividing it all by kilograms, so that only the kilograms cancel out. And I'm left with meters squared over seconds squared. This is not the units for a length. Our error comes into being right here, that I forgot to multiply by 9.8. So the units caught it. Plus, if I take the 50.77 nanometers and divide it by 7.2, we get a whopping 7 meters for the cat to make its distance on a 2.4 meter board. So even the value seems outlandishly large. So we'll take our answer, we'll divide it by the 9.8, and we'll see that the correct answer for this problem has x equal to 0.71 meters, and 0.71 meters is, as we go to our evaluate, I'm sorry, not evaluate. We've already got a number. Evaluate happened someplace up here. As we go to our review of our work, one, the units check. That's one of the things that we caught to help us realize we had made an algebra error. And the second thing is that, is this a reasonable value? Let's get to below. So from the center of mass, we had 1.22 meters to deal with. And our cat distance is actually within that range. So between the center of mass and 1.22, our 0.71 meters comes in that range. So we know it's reasonable because it's on the same scale as the board. The answer we had previously at 7 meters was just totally unrealistic. And the next thing to keep in mind is This is a rather light board, so I'm not surprised that what is that? 60-odd% of the way to the end of the board, the cat tips it. That kind of makes sense. All right, so this is a complete and correct version of the what's called the cat problem.